Hello everyone, welcome back to the NPTEL course on materials informatics. In today's lecture we will be talking about convolutions. So let us get started. So just as a brief recap, in the last session of both sort of theory lectures as well as Jupyter notebooks, we looked at the basic definitions of multilayer perceptrons as well as artificial neural networks. We saw what kind of tasks they can do, what complexities they bring in, what are the additional hyperparameters that you need to worry about, different optimizers and so on, and what kind of regularization strategies to use, right. And we also looked at examples of how to build neural networks in practice using both PyTorch as well as Keras. So in this lecture we will look at convolutions, and as before the schematics that I am going to be using in this lecture, unless otherwise mentioned, are from this book from Aurélien Geron. Okay. So what are convolutions, right? So convolutions as a mathematical idea has been known for a while, so since the 1950s or so, and the best way to sort of understand convolutions is by understanding how human vision basically works, right. So if you look at let us say an image of a house, right. So we basically recognize this as a house the first time, the very first time we actually see the house. So in other words, we do not need to see this house 10 times for us to recognize that it is actually a house, we only need to see it once, right. And the way that the sort of human vision system works is that our eyes basically takes in all the input visual inputs that we get, but the way our brain works is it sort of decomposes. So there is a part of the brain called the visual cortex, and it decomposes the same optical signal that it receives, which is the light that is being reflected from this house. It sort of decomposes that into different objects in an instantaneous fashion. So it decomposes into sort of straight lines, slant lines that are associated with this house, some kind of curved lines also, maybe once it decomposes that into simple shapes, it then puts together and tries to find more complicated shapes that are already present in the house. So for example, a triangle is a feature in this house. You also have these types of T junctions here that are part of this house, and then it tries to put together even more complicated objects, right. So initially the brain sees or receives all the inputs, right. Once it receives the inputs, it decomposes that into smaller level features or simple geometrical objects. It then considers combinations of these different geometrical objects, and it keeps increasing its complexity until it makes a final recognition that yes, this actually looks like a house and it does not look something like a fish, right. So that's in short how sort of visual cortex works, right. So our visual cortex or our human brain works in a hierarchical fashion. Whenever we see something, we decompose that into simple objects and then combinations of more and more complicated objects until we recognize the final object that we have in picture, right. This is in short how convolutions generally work. So convolutions are a way for hierarchical learning to be put into practice, right. So before we get to the mathematics or the technicalities behind convolutions, right, if you look at dense MLPs or dense neural networks in general, the way they are structured, they actually do not recognize all the features within an image, or more precisely they do not recognize the same feature in different parts of the image, right. So let us say you have a dense neural network. The way the dense neural network will recognize this house is that it will recognize this as a straight line, right, but this is a straight line in this part of the image, right. It will not recognize that this is actually the same straight line, right, or very similar straight line that is also in this part of the image. So in other words, the dense neural network will recognize that this is a straight line, this is a separate straight line, and these two separate straight lines formulate this image, rather than considering that these two lines are actually similar objects, right. So in other words, the decomposition is not very efficient in dense neural networks. So it does not recognize all the simple objects very well. It also does not recognize rotations or translations within images. So let us say you take the same image of the house, but then you translate the house to a slightly different portion of the same image, then the neural network does not recognize that it is the same house that has been translated, right. So there are limitations with how these dense neural networks sort of decompose features within an image, right. and this is why if you use dense architectures, so without without including convolutions, then you can have an explosion in the number of parameters. Right. So this is basically something like an image size. You can think of this as number of pixels of an image that you want to use in your training set. If your convolutional neural networks have a increase in number of parameters represented by this orange line here, your dense neural networks may have a very large increase, right, compared to your convolutional neural networks in terms of number of parameters that it is actually needing to recognize a given image. Right. So this makes the models very heavy and very cumbersome to train or even manage. Right. So convolutions are a very useful mathematical technique that is that sort of mimics how the human visual cortex learns. So it learns by decomposing a given image into smaller features of an image, and then it sort of combines the different features of the image to identify the final image. And the other powerful thing about human cortex is it also recognizes similarity in shapes across different parts of the image. So it recognizes that these two straight lines are similar. So that's another nice thing about the human visual cortex. So convolutions are a mathematical technique that sort of mimics the way the visual cortex works. So let's see how convolutional sort of neural network layers actually work, right. So here each neuron, unlike in a dense a neural network layer, each neuron is only connected to a certain number of neurons in its adjacent layer, and this number of neurons that it is connected to is what is referred to as the receptive field of this neuron, right. So for example, let us say this is the lowest layer, this is the input layer, this is the first hidden layer, right, and let us say you have bunch of neurons in the first hidden layer, right. So in a dense neural network, each neuron will be connected to every pixel of your input image, right, or every feature of your input layer, right. But in a convolutional neural network, right, your neuron, any given neuron only takes in information from a selective portion of the image. So it is only connected to the input features that are within its receptive field, right. So this enables the set of neurons here to only understand what is happening in a small portion of the image and decompose that image into simpler components, simpler components or configurations, right. And as you go up in the complexity, so as you go from the first hidden layer to the second hidden layer, neurons in the second hidden layer now only interact with or are connected to neurons that are within its own receptive field, right. So this neuron here, for example, can put together information that is learnt by this neuron as well as this neuron, right. So the left neuron here may have recognized that there is a straight line, there is a vertical line, there is a horizontal line, and there is also a T junction here. This neuron may have also come across this T junction here, right. So these two neurons have recognized the same T junction, but in two different sections of the image. But they do not interact by themselves, right. But the neuron above in the layer 2, so more in the upper layers, will be able to get the information from this neuron as well as this neuron, and hence it can put together the information that there are two T junctions, two similarly looking T junctions within the image, right. So as you keep going up in complexity, going up in the higher layers, higher levels of convolutional layers, neurons will be able to put together more and more information about the input image or your input data, and they will be able to make deductions that are of higher and higher complexity, right. So the objective of the lower layers is to decompose the image into smaller components, as small components as possible, and the objective of the higher layers is to capture in more and more complicated features, put configurations together and create maybe like shapes, right. So you can think of lower level features being lines, curves and so on, and upper level features being like shapes in an object, so eyes, petals, mouth, triangles, squares and so on, right. So this is in short how convolutional layers actually work. So they are different from dense neural networks in the sense that every neuron is not connected to every other neuron. Every neuron only interacts with neurons in its own receptive field. So it only reacts with a limited subset of neurons in its in the previous layer, in a layer that is lower to itself. Okay. So there are three sort of main steps in any convolutional neural network or a convolutional layer. So the first is the definition of your receptive field and what is referred to as stride. So in other words, let's say you have a receptive field and the receptive field has a bunch of neurons associated with them, right. So let's say you have a receptive field of 3 by 3 matrix, so that's a matrix size of 9. So you are basically going to interact with 9 neurons. How do you actually interact with the neurons, right? Do you take all the information at once or do you go step by step? So that is referred to as stride. So how are you actually scanning the data that is available in your receptive field, right? There is also filtering which we will get to later, and pooling which we will also get to a little later, maybe in today's lecture or in the follow up session, right. So receptive field and stride, so how neurons are interacting with neurons in its lower layer. Filtering, so filtering is a way to sort of recognize specific shapes or specific colors or specific features of a given input, and pooling is a way to accumulate all of them, is to basically ensure that you are getting the final output that you need, right. So these three are the main components in any convolutional process, right, and hence these three are the main components in a convolutional neural network as well, right. And once you go through these three processes, the eventual output that you get, right, can be passed through an activation function, right. In convolutional neural network you have the flexibility to have activation functions for each neuron within a convolutional layer itself, or you just have an activation function at the very end in your output. Both are possible, right, and that's a design choice that we have to make depending on the complexity of the problem, right. So convolutions, although they have fewer number of parameters compared to dense neural networks, so you would imagine that they do not need as much memory as dense neural networks, but they can still occupy a lot of memory simply because they need to do more mathematical operations on an average compared to the mathematical operations that you would need in a dense neural network, right. So the parameters are fewer, which is good, but you have a lot more mathematical operations, right. And since in convolutional networks you have fewer parameters than in dense neural networks, they have lower tendency to overfit. So in other words, these models have lower variance and higher bias compared to a dense neural network model. Okay, so let's look at some of these hyperparameters, right. So or some of the steps that are involved in a convolutional neural network. So the first two are basically the size of your receptive field and how do you stride or pad your data. So what is the size of your receptive field? So let's say you have let's say these two are two different convolutional layers, right. So you have the same number of neurons in both the layers. So you have about 1 2 3 4 5 6 7. So you have about 35 neurons in this layer here, and let's say this layer also has about 35 neurons, right. So if you now take the blue neuron here, it is connected to all the neurons that are highlighted by this blue box here, right. So all the neurons that are connected by this blue box is what is referred to as the receptive field, right. So typically if you imagine your convolutional neural network to be a stack of 2-dimensional rectangles or squares, you can define a width of your receptive field and you can also define a height of your receptive field, right. So in other words, you can define some kind of an area of your receptive field, right. So that is the definition of your receptive field. So how many neurons is any given neuron interacting with in its lower layer. Now what is referred to as striding, right. So striding is basically, so let's say you have a red neuron here and its receptive field is indicated by this, right, by this red box here. So it is also interacting with 9 neurons here, right. Now the blue neuron is adjacent to the red neuron, right, and it also has the same receptive field. So it has a receptive field of 9 neurons, right. But how or what will define the boundaries of this blue box, right. So you can either have a situation where you have the red and the blue boxes here in the lower layer offset by 1 dimension, right, offset by 1 neuron here, which is similar to what offset they have here, right. You can also have a situation where the red and the blue boxes are offset by 2 neurons, right, in the lower layer here. So which is what is indicated here, right. So in this convolutional layer, your blue and red are still adjacent neurons, but look at the blue and the red boxes, right. They are actually offset by 2 neuron units here, right, or they have a striding of 2. So here they have a striding of 1, here they have a striding of 2. You can also have situations where the red and the blue boxes do not overlap at all. So if you have a striding of 3, right, so the red and the blue boxes will actually lie next to each other and they won't overlap, right. So how are the receptive fields actually offset from one another in the lower layer for any convolutional layer is referred to as striding, right, and this is once again a very important hyperparameter. So you can define striding both in the width direction as well as in the height direction, right. So just like how you can define a width for your receptive field and a height for your receptive field, right. Receptive fields can also be asymmetric, so you don't have to have a 3 by 3 square all the time, right. You can also have a 2 by 3 square or a 3 by 1 rectangle and 2 by 3 rectangle, a 3 by 1 rectangle and so on, right. So you can define a striding as a striding height and a striding width and a receptive field height and a receptive field width. So that's the size of receptive field and striding. The final idea is what is referred to as padding, right. So let's say you have these two convolutional layers, right. So they are of both the same size, but if you take the receptive field of your red neuron here, you see that it is only covering 4 neurons in the lower layer, right. So this is actually the convolutional layer, right. It is only covering 4 neurons, right. So but it has a receptive field of 9, so which implies it's basically seeing or it's not able to get any information from 5 other neurons that it is supposed to get, right. So in order to make this mathematically easy, right, so I mean if you were to stick to this definition of your lower layer, right, your red neuron will have will be interacting with 4 neurons here, whereas your blue neuron here will be interacting with 6 neurons here. So you see that there is an asymmetry between how many neurons the red one is interacting with respect to how many neurons the blue one is interacting with. And this can cause some asymmetry problems in the way the network actually trains, right. So in order to reduce this kind of asymmetry, we can basically pad up the lower layers. So padding is basically we insert a set of dummy values around the lower convolutional layer such that each neuron in the upper layer is able to access symmetrically the same number of neurons in its lower layer, right. And when we do pad, so when we do add values to the lower convolutional layer, there are multiple choices that we can use for padding. So we can simply add zeros as dummy values, or we can take the mean of all the neurons here and then add the mean values here. We can take the median, or we can take median of the entire convolutional layer itself and then add it as the padding value here. So padding is another design choice that is often used to ensure that each neuron in the higher or upper layers are interacting with the same number of neurons in the lower layers, so that there is no asymmetry in how each individual neurons are interacting with. So size of receptive field, striding and padding are important things to keep in mind with respect to design of convolutional neural networks. So what is your size of your receptive field, how much you are going to stride, and are you going to pad, and if you are going to pad, how you are going to pad. Okay. So let's try to also get a visual sense of how convolutions look like, right. So this is a nice GIF image that helps you understand. So for example, each of these neurons here has a receptive field of a 3 by 3 matrix, right. So the first neuron basically scans through its receptive field of 3 by 3 matrices here and then assigns itself a value, right. How it assigns itself a value, we will get to that a little later. Same thing happens with the second neuron, same thing happens with the third neuron and so on, right. And here you see that the receptive field is a 3 by 3 matrix, the striding is a 1 by 0 matrix, right. So for example in the first row, so you see that the first and the second neurons in the first row only have striding along one of the axis, right. So there is no striding along the second axis as well. There is a striding in the second axis only when you create the second row of neurons here, right. So this is one example of how convolutions can work, and here we have not done any padding, right. So since we have not done any padding and we wanted to ensure each neuron is symmetrically interacting with the same number of neurons in its lower layer, we see that there are fewer neurons in the upper layer compared to the number of neurons in the lower layer. So in the lower layer we have 16 neurons here, so it's a 4 by 4 square, whereas in the upper layer we only have 3 neurons here. we can also create these convolutions in parallel, right. So we can have one section of the image being dealt with these sets of convolutional layers, another section of an image being dealt with these convolutional layers, and the third section being dealt with a different set of convolutional layers. Typically in sort of vision or image problems, we separate out the red pixels, the green pixels and the blue pixels, and then perform convolutions on the 3 different colors, for example, right. So there are different ways that we can do convolutions. So but the key thing to keep in mind is that the value of any given neuron will depend on the receptive field. So the values of all the neurons, the values that the neurons are outputting in its receptive field, and we have to find a way to sort of assign a value to that neuron as well. Okay. Now let us move on to another important idea in convolutional neural networks, which are referred to as filters, right. So what is a filter? A filter is basically the kinds of features that the model is actually trying to learn from a given image or a given input. So let us take an example of this image, right. So if you have what is referred to as a vertical filter, right. So what this vertical filter tries to do is it tries to filter out vertical white lines in this image, right. So if you were to perform convolution, so you take this as an input, you pass this filter, right, during your convolutions. So each time a neuron scans through its receptive field, it multiplies this filter as well, right. So it will scan through its receptive field and only identify the vertical white lines, right. So that is the objective of this filter. So if you pass through a filter, you may see that the resultant image, what we refer to as a feature map here, is enhancing all the vertical white lines in this image, right. So all the other features get blurred out. So all the horizontal lines or vertical black lines get blurred out, only the vertical white lines get enhanced, right. So this is a way of isolating a certain set of features in a given image. You can do a same exercise for highlighting all the horizontal white lines as well, right. So if you put through this horizontal features, you see that this white line and these white lines here get magnified or get enhanced more, and the remaining features sort of get blurred out a little more, right. So filters are a very important way to identify which features are important in a given image or in a given input, right. Typically when we design convolutional neural networks, we number of filters and the size of each filter are two things that we try to define. So number of filters is, so let us say I have this input image, I only want to identify the vertical white lines and the horizontal white lines, then I define 2 filters, right. If I also want to identify slanted white lines, then I will define a third filter, right. So the number of filters is something that is a hyperparameter that we have to choose, and the size of each filter. So you see that each filter is a very small pixel, right. So it's probably, this is maybe a 2 by 2 pixel, something like that. So the size of a filter is something that we can define, right. So we can define larger filters which will help us identify even larger features, right, within a given image. But the number and the size is what we try to define in a convolutional neural network. The actual filter itself, we actually allow the model to learn by itself. Right. So in this case, maybe we say that identify 2 by 2 pixels and identify 2 filters that are most relevant, and the model itself will try to identify, let me try to identify all the white lines, vertical white lines, and let me try to identify all the horizontal white lines, right. So that's how the model may react, or the model may try to learn the important features, right. So what filters the model is actually using, you will allow the model to learn by itself, but the number of filters or the number of features that the model is learning and the size of each feature, that is something that is a hyperparameter that you can tune. So filters are very important in convolutional neural network, and there are a couple of important things to note, right. So one way in vision problems that we use filters is to have filters for different images, right, have filters for different colors. So you can have filters for red color, green color, blue color and so on, which will isolate all the red pixels, all the green pixels, all the blue pixels separately in your image. you can also have filters to identify certain features, right. So for example, this filter identifies a black line within a pink pixel, this identifies a horizontal black line within a blue pixel, and so on. And you can also have more and more complicated filters. So this identifies as a pink square within a blue rectangle. This identifies 3 different rectangles, right. So one blue, one pink, and one green, and so on, right. So the specific filters are learned by the model, but the number of filters and the size of the filter, the dimension of this filter, is a hyperparameter that we can define, right. And if we have in any given convolutional layer, if we give the model certain number of filters, for each filter we will basically create a feature map, we will basically create a layer, right. So our input image may be a single layer, but the more filters we use, the more layers we actually stack up, or the more maps we actually stack up in a given convolutional layer. So your convolutional layer is no longer a 2-dimensional object, it is actually a 3-dimensional object, right. So for one filter you just get one map, right. For 2 filters you get 2 maps, for 3 filters you get 3 maps, and so on. The stack of these 3 maps is basically your convolutional layer, right. And every convolutional layer that is above gets access to all the maps, right, in its previous layer, in its lower layer, right. So this neuron, for example, will not just interact with the neurons in the receptive field of the first map here, it will interact with all the neurons within its receptive field across all the maps, right. So you see that information can get transmitted quite quickly and transmitted very efficiently, right. So in other words, let us say some of the maps are putting together these horizontal lines, vertical lines, and so on. You can now design these more and more complicated features in a more easy fashion, right, or the model itself can design its own complicated features in a fairly systematic, fairly easy fashion, right. So just to point out, so a given filter's receptive field extends over all feature maps, so all feature maps of the previous convolutional layer. So the stack of these maps is one convolutional layer, right. And just a couple of other things to note, each feature map itself, right, all the neurons within a feature map share the same sets of weights and biases, right. So each neuron within a map have identical weights and biases, they do not have their own independent weights and biases, and this helps in a large extent to prevent parameter explosion. So if each neuron in a given map has its own weights and biases, then you are going to have, so let us say you have 100 neurons in a given map, right. For each map you are going to have 100 different weights and biases, right, and depending on the receptive field also of each neuron, right. So the number of parameters is going to explode very quickly. So what we instead do is, for each map we have the same set of weights and biases, and for different maps you can have different weights and biases, right. So in map 2 neurons can have different sets of weights and biases, but all neurons within that map will have the same set of weights and biases, and in map 1 they will have their own set of weights and biases as well, right. So each feature map has its own set of weights and biases, and it generally prevents explosion of features. It also enables detection of a given feature along in anywhere in the figure itself. So what these filters enable to do is that, so let us say you have created a filter that is recognizing black lines within a blue pixel, right. As long as this filter has been created, your neural network will be able to recognize any instance of a black line on a blue pixel at any point in your image, right. So one filter is enough to recognize that same feature across your entire image, right, whereas in a dense neural network you basically need to your model needs to recognize the black line on a blue pixel or different parts of the model will recognize the black line in the blue pixel that are coming in different in different parts of the image, right. So if you have 2 different instances of a black line on a blue pixel, that will be learnt as a black line on a blue pixel by 2 different parts of the deep neural network model. Whereas filters, what they allow you to do is that the models can actually learn from one another, right, or the neurons can learn from one another. So the model itself will be able to recognize the same feature across different portions of the same image, of the same input, right. So this also helps convolutional neural networks to be more data efficient, so they can learn more quickly with limited amounts of data, right. So filters help with reduction of parameter explosion, and they also help in learning similar sets of features across different parts of the same image. Okay. The number and complexity of filters also increases with the number of layers. So if you take a simple image of a dog for example, in the first few convolutional layers maybe you are recognizing simple features like lines, curves, maybe different colors and so on. And if you go to the second layer for example, maybe the filters become more complicated, you are understanding textures, and then finally if you increase further in complexity, maybe you recognize parts of your dog. So you recognize eyes, you recognize nose and so on, right. So the sort of complexity of the filters in general increases with the number of layers in your convolutional neural network. The number of filters also increases with the number of convolutional with the convolutional layers. So for example, each block, the width of each block here indicates the number of filters you have. Initially you have fewer filters, here you have more filters, and here you have even more filters. So this one block basically refers to one convolutional layer or a collection of feature maps, right. So the final layers have a very large number of filters, middle layer has a reasonably moderate amount of filters, this has lower number of filters, right. So number and complexity of filters keeps increasing with increase in number of layers, right. Let's now understand what is the final important operation within convolutional neural networks, which is basically what is referred to as pooling. So think of pooling as a way to shrink your output. So if you want to reduce the size of this image, right, or sort of compress this image into fewer pixels without losing key features of the image, you would think of some kind of a compression algorithm to do that, right. So pooling basically helps you do that in a convolutional neural network. So in other words, it tries to reduce the amount of information without significant loss in the amount of information itself as an increase in the number of layers in your convolutional neural network. So for example, let's say you have a lower layer that is fairly big, right. So each I mean you are basically storing in a lot of information here about the pixels in each of the neurons here. Now you can create a pooling operation where you are trying to reduce all of this information in the lower neural network into a very small neural network here, which is a 3×4 layer, right. So you have 3 neurons here, 4 neurons here, so it's about 12 neurons here, right. So from a very large convolutional layer, you are trying to reduce the amount of information to a smaller convolutional layer without resulting in a significant loss in the amount of information. So one common way that you can actually compress this information is to do what is referred to as a pooling operation, or specifically a max pooling operation. So let's say this red neuron has a receptive field of a 2×2 matrix here, right, and let's say the values coming from the neurons are 1, 5, 3 and 2. You can do what is referred to as a max pooling, or just take the maximum value among the 4 values that are being present here. So you assign this value to be 5. Right. Same thing you do for this blue neuron, same thing you do for this black neuron and so on, purple neuron and so on. And if you do the same, you may end up with a more narrower representation or a smaller representation of the same information that you had in the lower convolutional layer, right. So pooling is a very common operation that is normally used, and the type of pooling is that is typically used is a max pooling operation. Okay. And one other sort of important thing to note is that pooling can also regularize your convolutional neural network because it reduces the amount of redundant information that you are actually storing in your neural network, and it can also add in translational invariance. What I mean to say is, so let's say you have in your lower layer you have 3 different representations, right. So these are basically block representations of A, B and C, and you see that A, B and C are nothing but the same objects, but they are translated. So B is shifted from A by one pixel here, C is shifted from B by another pixel here. So if you use a pooling operation, you see that A and B are basically have the identical representations, right, after you do max pooling here, whereas C has a slightly different representation. So it introduces some amount of translational invariance, so you can continue to recognize the same kind of objects when you do pooling operations if they are translated by a small extent. So that's one another nice thing to note about pooling. So just putting together everything, so you combine a receptive field and a filter. So filter is also referred to as a kernel commonly in convolutional neural networks, and you have a pooling operation, you can also put in an activation function within your pooling operation. So instead of taking a max pool, you can have an activation function as well. So a receptive field plus a filter plus pooling is basically your convolution, right. So let us say you have this information here. So first is your definition of your receptive field, you extract this matrix, you multiply that with your filter, whatever you want to recognize, and that is your resultant matrix value here. You can do something like a sum pooling here, or take a summation of the values here, and then you have a representation of your final neuron here, right. So in other words, you have converted the representation of this 7 by 7 matrix here into a simpler 5 by 5 matrix, with highlighting this type of a filter, right. So that is what you do in a simple convolutional operation. And just to give a sense of how max pooling works, so let us say you have a convolutional layer that looks like this, you do a simple max pooling operation with a receptive field of 2 by 2, you see that you will take the first maximum blue value here, which is 5, maximum green value here, which is 9, red value which is 9, and orange value which is 8 here. So this is how a simple max pooling operation works. Here we do a sum operation here, so we take the sum of element wise sum of all the values in our matrix here, right. So combination of receptive field, filter and pooling with an activation function is usually referred to as a convolution operation. Okay. So how do typical convolutional neural networks look like? So they look like this. So you have an input, you pass it through a certain number of convolutions, then you typically do a pooling operation, then you pass through convolutions, pooling and so on, right. So after a final set of pooling operations, you typically get a flattened vector of flattened vector of numerical values, which is considered to be a representation of your image, right. And once you get this flattened network, you can then pass it on to a simple dense neural network, a dense MLP, and perform tasks. The tasks could be classification, the task could also be regression. So if it is not a visual image, maybe you want to do regression tasks, right. If you want to take a more granular sort of look, so you see that initially you have this may be your input layers, you have a pooling layer here, and then you have you are changing the number of filters in your second convolutional layer, you do another pooling operation, change the number of filters, you have more feature maps here, this is your third convolutional layer, another pooling operation, fourth convolutional layer, another pooling option, then the final convolutional layer, and then this pooling operation basically flattens your representation of your convolutional network into a single vector, which you then pass down to a multi-layer perceptron or a dense neural network. So this is how a typical convolutional neural network architecture looks like. And just to wrap up things quickly, so we can also visualize convolutional neural networks using this GIF image here. So it gives you a sense of how the convolution operation actually does, right. So if we allow the GIF to start, so you see that initially you do a striding operation multiplied by a kernel, so this is your filter operation, you get a certain output, and then from the output you do a pooling operation, right. So the pooling operation creates a smaller representation, you flatten it, and then you pass it on to a fully connected neural network, and finally you get an output, right. So this is in short how convolutional neural networks actually work. So these are the mathematical operations that are actually done under the hood in any convolutional neural network. Okay. So how do you construct convolutional neural networks with Keras and PyTorch? So with Keras you can import this class called convolutional 2D. So it basically creates a 2-dimensional convolutional neural network, very good for images, right. Max pooling basically refers to a pooling operation on 2-dimensional matrices, right. So you can create an instance of convolutional 2D layers. So just like you created instances of sequential layers before, you create dense layers before, you create instances of convolutional layers, and here you put in the additional hyperparameters. So how many filters you want, what is the filter size, what is your stride, what kind of padding you want to use. So here it says same padding, so it'll take the same value as the neighboring neuron or pixel, and then what kind of activation function you want, right. And then you would also define what is your how do you want to do your pooling. So you do a max pooling of your 2D matrices, you take a pool size of 2, right, and then you add this convolutional layer, and your pooling layer, and once you add a certain number of convolutional pooling layers, you can then add a flattening a flattened layer which will flatten out all the representation which will flatten out your 2D matrix basically into a single vector, and then you can pass that on to a simple convolution simple dense neural network. In the case of PyTorch, you once again have a similar kind of function here called convolutional 2D, and this again takes in similar sets of hyperparameters. So it takes number of inputs, number of outputs, filter size, and so on. Yeah. So and in your pooling operation here is in the case of PyTorch is usually found under functional, and it's not a layer by itself in the PyTorch definition, but in Keras definition it's part of the layers layers collection. Okay, with that let's summarize today's lecture. So we looked at convolutions as a way to efficiently create linear neural networks. So these can create more sparser networks. So each neuron is not connected to every other neuron in its lower layer, it's only connected to a receptive field, right? But this helps in distinctly in hierarchical learning, and it helps us both decompose a given image into smaller set of features, and it also helps us reassemble these features into more complicated textures, shapes, and so on. And the key things to keep in mind with any convolutional neural network or any convolutional mathematical operation is we have to define a receptive field and associated striding and padding. We have to define what kind of filters we want to use. So filters help us identify important features within a given input data, and what kind of pooling. So how do we want to minimize the amount of data that is being stored, right, or find linear representations of whatever input data that we have. Convolutional neural networks generally works well for any structured data. I gave examples of images, but it also works well for text data as well, and we will soon see that principles of convolutions are very important when it comes to representing materials as well, representing crystal structures as well. And some of the important hyperparameters that we considered are the receptive field size, number of filters, type of pooling, and padding. And with this we are ready to go to the next topic, which will be on graph networks, and graph networks play a very important role in modeling of materials and crystal structures. I'll just show a brief glimpse of the important functions or classes that we came across in our neural network discussions, as well as in our convolutional discussions in the slide below here. So we see that these are the different classes and functions that we used for building neural networks and also building convolutional neural networks in Keras as well as in PyTorch. So with that, I thank you all for joining today's lecture. I'll see you all in the next one.